Imagine a lump of rock, no bigger than a potato, nestled in the pitch-black depths of the ocean, 5,000 meters below the surface, where sunlight has never dared to venture, and pressures could crumple steel like paper. This unassuming chunk, cloaked in the icy embrace of the abyss, holds secrets so staggering they could rewrite the very laws of nature. Scientists stumbled upon something down there that defies belief, a discovery so wild it sparked a frenzy among governments, billionaires and researchers alike. Estimated to be worth over $3 trillion, this isn't just a treasure trove of metals that could power every electric vehicle on Earth. No, it's something far stranger, something that pulses with a mystery that could unravel the origins of life itself. What they found in the ocean's darkest corners is beyond anything anyone could have dreamed, and it's shaking the foundations of everything we thought we knew. The journey begins in the Clarion-Clipperton Zone, a sprawling, uncharted wilderness, stretching across 4.5 million square kilometers of the Pacific Ocean, nestled between the sun-soaked shores of Hawaii and the rugged coast of Mexico. This is no ordinary place. It's a realm so alien, it might as well be another planet. The seafloor here plunges to depths of 5,500 meters, where temperatures hover just above freezing, and the pressure is 500 times greater than at sea level. No light pierces this void, no warmth softens its grip. It's a place where time itself seems to stand still, a frozen snapshot of Earth's ancient past. For decades, this desolate plain was little more than a curiosity, eyed by mining companies for its scattered riches, nodules of copper, nickel, cobalt and manganese, metals so valuable they could fuel the Green Revolution. But in 2021, a team of scientists set out with a different mission, one that would uncover a truth far more profound than any mineral wealth. Their goal was simple yet vital: to understand how oxygen, the lifeblood of our planet, cycles through the deep sea's murky sediments. These muddy plains, though lifeless to the untrained eye, teem with microscopic organisms that somehow thrive in this hostile world, sipping on the faint wisps of oxygen that drift down from the surface. By studying how these creatures breathe, the team hoped to unlock the secrets of deep-sea ecosystems and gauge how human activities, like mining, might disrupt them. Armed with cutting-edge technology, they deployed robotic labs called landers, self-contained marvels that sink to the ocean floor and conduct experiments in the crushing dark. These landers carried benthic chambers, sealed containers that trap samples of mud and seawater, and oxygen sensors to measure how quickly the microbes consume their precious air. The plan was straightforward: track the oxygen levels, map the biological activity, and piece together the puzzle of life in the abyss. But the ocean had other plans. When the first readings came back, they were nonsense. The sensors showed something impossible. Oxygen levels inside the chambers weren't dropping as expected. They were rising. Microbes should have been gobbling up the oxygen, leaving less behind, but instead, the chambers were filling with it, as if the seafloor itself was exhaling. The team's initial reaction was disbelief. Instruments fail in these conditions all the time. Salt water corrodes circuits, pressure warps metal, and the cold plays havoc with electronics. They recalibrated the sensors, ran the tests again, and sent new landers to different spots across the zone. But no matter what they did, the results held firm. Oxygen was appearing where it had no right to be. After 5 years of relentless testing across multiple expeditions, the truth was undeniable. Something in the total darkness of the ocean's basement was defying the fundamental rules of science. This wasn't just a glitch. It was a revelation that turned everything upside down. For centuries, we've known that oxygen comes from photosynthesis, the process where plants and algae use sunlight to split water molecules, releasing oxygen as a byproduct. But here, 5,000 meters below the surface, where no light has ever shone, something else was at work. The team was forced to consider radical possibilities. Could certain minerals be reacting with seawater to release oxygen? Was there an unknown chemical process at play? Or most tantalizing of all, could there be a form of life so alien it produces oxygen in ways we've never imagined? The implications were staggering. If oxygen could form without sunlight or living organisms, it would challenge our understanding of how deep-sea ecosystems function. It might even explain how life clung to existence in Earth's early days, when the atmosphere was a toxic soup devoid of oxygen. More thrilling still, it could open the door to finding life on distant ocean worlds like Europa or Enceladus, where sunlight never reaches but chemical processes might sustain alien ecosystems. The Clarion-Clipperton Zone, once seen as a goldmine for metals, transformed overnight into a natural laboratory, a window into processes we never knew existed. Those potato-sized nodules, long prized for their economic value, suddenly took on a new role. Could they be the key to this mystery? Were they interacting with seawater in ways no one had predicted? The discovery was a stark reminder that even in an age of satellites and supercomputers, the deep ocean remains one of Earth's last great frontiers, a place where the rules we take for granted can be rewritten in an instant. As the team pored over the latest data from their deep-sea drones, another shock awaited. The seafloor wasn't just producing oxygen, it was reshaping itself in ways that defied all logic. Beneath 5,000 meters of crushing water, the muddy plain was carving itself into intricate geometric patterns, as precise as anything crafted by human hands. Spirals unfurled like the shells of ancient nautiluses, grids formed with near-perfect 90-degree angles, and interlocking ridges created tessellations that would make mathematicians weep. These weren't the random scars of erosion or the chaotic deposits of sediment. The patterns were deliberate, purposeful, as if the seabed had decided to become something more. Comparing images taken just hours apart, the team watched in stunned silence as the shapes evolved. Ridges stretched like growing crystals, grids expanded their boundaries, and spirals tightened their curves, all with a glacial patience that spoke of something vast and ancient at work. The electromagnetic data only deepened the enigma. Tiny fluctuations in the local magnetic field mirrored each subtle shift in the patterns, hinting at a hidden connection between form and energy. The changes followed a rhythm, a pulse of energy, a movement, then silence, repeating like the heartbeat of a sleeping giant. The team ruled out every conventional explanation. No hydrothermal vents spewed heat, no tidal currents stirred the sediment, no chemical emissions left a trace. Whatever was sculpting the ocean floor operated outside the known laws of geology, leaving undeniable physical evidence, but no clear cause. Then came the final, chilling detail. Old survey maps, buried in archives from decades past, revealed that these patterns weren't new. They were simpler back then, less distinct, but they were there, growing and evolving under humanity's nose for who knows how long. And now, with cameras trained on them, the patterns seemed to shift faster, as if aware they were being watched. In the control room, a question hung heavy in the air. Were the scientists merely observing, or were they somehow part of this strange dance? Faced with the impossible, the team turned to the most logical suspect: life. The deep sea, harsh as it is no stranger to the bizarre. Microbes thrive in places that would kill most creatures: beneath Arctic ice, inside boiling hydrothermal vents, even within the Earth's crust. Many of these organisms don't need oxygen or sunlight, drawing energy from sulfur, methane, or iron instead. Could a strange new microbe, hidden in the Clarion-Clipperton Zone's sediments, be producing oxygen in some unheard-of way? To test this, the team took a drastic step. They sterilized the benthic chambers, dousing them with biocides designed to wipe out every trace of life. These chemicals shred cell membranes and disrupt metabolism, ensuring no microbe could survive. The treated chambers were lowered back to the seafloor, and the sensors began their silent vigil. If microbes were the culprits, the oxygen levels should stabilize or drop. But when the data came back, it was a gut punch. The oxygen levels in the sterile chambers rose just as before, slow and steady, defying every expectation. This was no longer a quirk or a malfunction. It was a phenomenon, consistent and repeatable across controlled experiments. The team doubled down, running more tests, varying the sterilization methods, and moving the chambers to different parts of the zone. Yet the results never wavered. Oxygen was appearing and life wasn't the cause. The mystery grew darker, more urgent. The team reached out to geologists, chemists, and deep-sea biologists, scouring historical data and comparing notes. Could a chemical reaction between the sediment and seawater be responsible? Was there a process no one had noticed before? The absence of a biological explanation was unnerving. In the ocean, life is often the wild card, the source of unexpected twists. But with microbes ruled out, the team faced a reality that felt almost supernatural. They were witnessing a process unlike anything science had encountered, a ghost in the data that refused to be explained. Then, a clue emerged from an unlikely source. During a conference on deep-sea mining, a passing comment stopped the team in their tracks. A speaker described the metallic nodules on the ocean floor as batteries in a rock, a metaphor for their complex mineral behavior. It was a throwaway line, but it sparked a revelation. The team had been studying these nodules for their oxygen readings. But what if the nodules themselves were active, not just passive lumps of metal? Tests revealed something astonishing. Under certain conditions, the nodules generated tiny electrical currents when exposed to seawater. These currents, though faint, were enough to suggest a new possibility. The nodules weren't just geological relics, they were dynamic, interacting with their environment in ways that could reshape our understanding of the deep sea. This discovery opened a floodgate of questions. What role did these currents play in the bizarre ecosystems of the abyss? How did they affect the chemistry of the surrounding water? And, most critically, what would happen if mining companies stripped these nodules from the sea floor? The comment about batteries in a rock was more literal than anyone had imagined, a reminder that the ocean still holds secrets we're only beginning to grasp. The team wasn't ready to make bold claims. The science was too new, the phenomenon too slippery, but the nodules had shifted from background noise to the heart of their investigation. They had a lead, not an answer, and in science, that's often the most exciting place to be. Back on the research vessel, floating hundreds of kilometers from the nearest shore, Another anomaly surfaced during routine diagnostics. The equipment picked up a faint, steady electric signal, about 1 volt, barely enough to notice, but impossible to ignore in a place where nothing should be generating energy. No power sources, no large organisms, no heat or movement could explain it. The team ran checks, swapped out gear, and retested, but the signal persisted, a quiet hum from the void. This wasn't just a curiosity, it was a hint of something profound. Even a small voltage can drive chemical reactions, like rust forming on metal or life-sustaining compounds bubbling from hydrothermal vents. But here, in the stable, predictable conditions of the deep sea, the source of this voltage was a complete mystery. No moving parts, no temperature gradients, nothing fit the models. The seafloor itself seemed to be wiring itself, conducting energy in ways that defied explanation. Whispers spread among the crew about electrochemical reactions unique to the extreme pressures of the abyss, processes that might only occur 5,000 meters down. The scientific community was cautious. No one wanted to jump to conclusions, but the implications were electrifying. If the deep sea could generate energy naturally, in ways we don't yet understand, it could transform our view of the ocean floor from a dead archive to a living, dynamic system. That single volt, rising silently from the darkness, became the loudest signal of all. A beacon, pointing to possibilities that stretched far beyond the team's original mission. The pieces began to come together, revealing one of nature's best-kept secrets. The seafloor's metallic nodules were acting as natural batteries, breathing oxygen into the ocean without sunlight or life. In the Clarion-Clipperton Zone, these potato-sized rocks, packed with manganese, nickel, cobalt, and copper, were doing something extraordinary. When exposed to seawater under the immense pressure of the deep, their unique composition generated tiny electrical currents, just strong enough to split water molecules into oxygen and hydrogen through a process called electrolysis. This wasn't biology, it was pure geochemistry, a trick of physics and chemistry played out in the ocean's high-pressure laboratory. The oxygen bubbled slowly into the surrounding water, while the hydrogen drifted away, leaving behind a phenomenon that no one had anticipated. This dark oxygen production, as the team dubbed it, was a game-changer. For marine scientists, it suggested that deep-sea ecosystems might rely on oxygen sources we never suspected, supporting life in ways we don't fully understand. For astronomers, it raised tantalizing possibilities about ocean worlds like Europa, where metal-rich seafloors might produce oxygen without sunlight, creating conditions for life. For geochemists, it demanded a rethink of Earth's ancient oceans, where similar processes could have sustained life before photosynthesis evolved. But the discovery also carried a warning. These nodules, the heart of this newfound process, are the same ones targeted by deep-sea mining companies. The Clarion-Clipperton Zone is ground zero for their ambitions, with plans to harvest these rocks for the metals that power electric vehicles and renewable energy. Disrupting the nodules could alter oxygen levels that deep-sea creatures have depended on for millennia, with consequences we can't yet predict for one of Earth's last pristine ecosystems. The stakes couldn't be higher. This isn't just a scientific curiosity. It's a fundamental Earth process, hidden in plain sight until now. The nodules, once dismissed as inert, are now seen as vital cogs in a delicate machine, one we're only beginning to understand. Mining them could be like pulling the plug on a system we didn't know existed. potentially wiping out ecosystems before we even catalogue them. The team's findings have sent shockwaves through the scientific community, forcing a re-evaluation of how oxygen moves through the ocean's depths and what it means for life on Earth and beyond. The deep sea, long thought to be a barren wasteland, is proving to be a vibrant, enigmatic world, pulsing with secrets that challenge our every assumption. The discovery of dark oxygen has rewritten the rules of ocean science. Oxygen, the cornerstone of most life, can now form without sunlight, photosynthesis, or living organisms, driven by the quiet energy of mineral-rich rocks. This chemical process, unseen until now, opens up possibilities that stretch across disciplines. If oxygen can emerge in the darkest, most extreme corners of our planet, what might be possible on Mars, Europa, or Enceladus, worlds once thought too harsh for life? The irony is that the very nodules driving this process are at the heart of a looming conflict. Mining companies see them as the key to a sustainable future, their metals fueling the batteries and infrastructure of a green economy. But harvesting them could destroy a natural oxygen source we're only beginning to comprehend, potentially unraveling ecosystems that have thrived in the dark for eons. What began as a routine study of seafloor oxygen has become a race against time. Scientists are scrambling to learn more about this hidden system before it's altered forever. The deep sea, once dismissed as a lifeless desert, is revealing itself to be a dynamic, mysterious realm, far more alive than anyone imagined. 5,000 meters below the surface, in the silent crush of the abyss, we may have found the key to understanding life, not just on Earth, but across the cosmos. What scientists discovered is nothing short of insane, a revelation that demands we tread carefully. The ocean's depths hold answers to questions we haven't even learned to ask, and it's up to us to decide what happens next. If oxygen can form in the darkest reaches of our seas, could it exist elsewhere in the solar system? The possibilities are as vast as the ocean itself, and the answers lie waiting in the shadows below.